Howdy, welcome to Math 153, Elementary Statistics. I am Lance Curtis, and this is the lecture for sections 10.4 and 10.5. You can see section 4 of chapter 10 gets into prediction intervals and variation. So let's dive in. Key concepts in this section are to present methods for constructing a prediction interval. Okay, now we're kind of familiar with the concept of intervals. We've already dealt with confidence intervals back in chapter 7, but prediction intervals are a little bit different from confidence intervals. They are similar, but they're not the same. Both prediction intervals and confidence intervals have upper and lower limits. They both depend on a confidence level. However, confidence intervals center around a population parameter, such as the proportion, the mean, standard deviation, whereas a prediction interval centers around a single data point in the population. So whereas we're looking at some sort of parameter that describes the population as a whole when we make a confidence interval, with a prediction interval, we're looking at an individual member of the population. Prediction intervals simply place a confidence level around a predicted value that we produce with the regression equation. So for each fixed value of x, corresponding sample values of y are normally distributed about the regression line with the same variance. That means that for a fixed and known x naught, so x naught is just simply some x value that we pick from the population, the prediction interval for an individual y value is what you see here on the screen, y hat minus e less than y hat plus e. The margin of error for the prediction interval is what you see here, this nasty beastly equation thing, which has a new variable attached to it. This s sub e is the standard error estimate, and it's given by another nasty radical equation, though not as nasty as the one for the margin of error. And of course, it's the sample size, and these x values here come from your sample data, where x naught is actually the x value that you're using to make your prediction. Note the n minus 2 degrees of freedom on your standard error estimate. That becomes important. So when you go to calculate your critical t value to get your margin of error, you need to use n minus 2 degrees of freedom. Let's go back and look at this example that we've seen previously, where we correlated shoe print length and height. We previously found the linear regression equation, and you see that equation at the bottom of the screen, y hat equals 128.91 plus 1.63x. This equation describes the relationship between shoe print length and height. So if we're given a shoe print length of 29 centimeters, what is the 95% prediction interval for height? Well, first we need to find the standard error, S sub e, but to do that, we first need to find the sum of the differences between actual and predicted values for y. So here we have a table of our actual data set that we used to make our model, our linear regression equation. These are actual measurements for y. Now, the predicted measurements for y hat, come when we take the x values and put them into the regression equation. So if I take 29.7, which is my first x value there in the table, and I put that into my regression equation, multiply by 1.63 and then add 128.91, out comes 177.3. That's the predicted value. I do that for each of the x values in my data set. So now I have another row that's listing values for predicted y, or y hat. I can then take the difference between the actual y values and the predicted y values for each of my sample pairs. So you see that for the first example, 175.3 minus 177.3 yields a negative 2.0. I do that for each of the pairs of y's in my data set. Now, if I square each of those differences, I get the extra column that you just seen come up onto the screen. If I then take all of these squares of differences and I add them together, I get 29.45. This is the sum of the squares of the differences between the actual predicted y values. This is a value that I need to calculate my standard error, as you see in the equation here on the screen. So now I just substitute in what I know. I have a sample size of 10, so therefore 10 minus 2 is on the bottom, 29.45 on the top. Divide out, take the square root, and out comes 1.919. This is my standard error estimate. Now that I have the standard error estimate, I can find the margin of error E. So here's my general form of the equation. Notice that I get my t value by using n minus 2 degrees of freedom. So 8 degrees of freedom, 95% prediction interval, so I want 95% on a two-tailed t distribution. That's going to give me 2.306 for my critical value. 1.919 is the standard error that we just calculated. And the other values that you see substituted in the equation come from the data set itself. So the x naught is the 29 that I was given to find an estimate for the prediction interval. X bar is simply the mean of all the x values, so that's 29.57. If I sum all the x values together and then square that sum, I get 295.7. And then if I square each of the x values and then add them together, I get 8,771.63. So punch this out on the calculator, and out comes 4.67. Now I have everything I need to substitute into the general form for the prediction interval. Here's the general form. I substitute in, so my predicted value with the 29 centimeters that I was given, I put that into my regression equation, and that's where the 176.28 comes from. And then the margin of error E, we just calculated 4.67. So I subtract on the one side, add on the other, and I get a prediction interval of 171.61 to 180.95. What this says is that we are 95% confident that the true value that corresponds with 29 centimeters is somewhere in this range. So the height of the individual with who has a shoe print length of 29 centimeters is somewhere between 171.61 and 180.95. This is a fairly large range of values for height. So a single shoe print doesn't really tell us much about a person's height, because we can't really narrow it down to something that's actually useful. It's a difference of, almost 10 centimeters. That's pretty considerable. So this doesn't really tell us a whole lot about a person's height. We need something that gives us a tighter range of values in order to make a very useful prediction from it. This brings us to the concept of explained and unexplained variation. Again, let's use our shoe print and height data set to illustrate this concept. And so here on the screen, you're seeing a scatter plot of the 10 data points that we use to make our regression equation. The slanted red line in the middle of the scatter plot is the regression equation. This is the line that best fit for the data points. The horizontal red line that you see is the actual mean value of the y's. The reason why there's the two lines are on your scatter plot is because we have two possible choices for making predictions. Okay, one is the regression model. Okay, if it's good enough for making predictions, and we know it's good enough if its R value is greater than the critical R value, then we know it's good for making predictions, and we can use the model to make a prediction. If the model is not good for making prediction, then we're going to use the mean value of the y to make our prediction. That's going to be our best estimate when the regression model is not good for making predictions. So here you have these two lines imposed upon the scatter plot for our data. Now, each of these individual data points has a different deviation from each of these lines. So, for example, let's look at this data point up here towards the top of the scatter plot. 30.6, 181.6. Okay, so the X value, or the shoe print length, for this data point is 30.6 centimeters. The height for this data point, or the Y value, is 181.6. Explained deviation is then the difference between the regression line and the mean value line that corresponds with that individual data point. So you can see that the distance that's marked out by the arrows is directly in line. So if I just extend those arrows vertically, I'll intercept that data point. Okay, so I want the vertical distance that's between those two regression lines that corresponds with that data point. That's the explained deviation. And the reason why it's explained is because we know where those lines come from. We know that the regression line comes from the X and Y values of the individual data points. And we know that the mean value comes from the Y values that are in our data set. So we know where that difference comes from because we can explain where each of those values comes from. Contrast that with unexplained deviation, which is the difference between our actual Y value and the regression line. This difference is unexplained because we don't really have an explanation for the actual value. We have an explanation for the predicted value. We know where the regression line comes from, but we don't know exactly where the height of 181.6 comes from. So this difference is called the unexplained deviation. The total deviation is just the distance between the data point and the mean. Or, as you can see from the graphical explanation on the scatter plot, the total deviation is the sum of the unexplained and explained deviations. We add them both together and we get total deviation. Let's look at another data point towards the bottom. So the data point that we just looked at is above the regression line. Now let's look at a point that's below the regression line. Do these definitions still hold? The answer is yes. The explained deviation is the distance between the regression line and the mean. So that's going to be located here for this data point, 28.4, 174. The unexplained deviation is the distance between the regression line and the data point. And then the total deviation is the distance between the data point and the mean. It's also the sum of the explained and unexplained deviations. How does this work out when you actually put actual numbers into it? So here I have the same scatter plot, same data points, and I have the regression line and the mean line. So let's look first at the data point that we looked at first. 30.6, 181.6. So if I imagine going vertically down, the corresponding points on the regression line will be 30.6, 178.2. Okay, the X value stays the same because I'm just going vertically straight down. The Y value is going to change, and that Y value I get by putting the X value into my regression equation. I can go further and find the corresponding point on the mean line, 30.6, 177.2. Okay, the X value stays the same, and the Y value is set by the mean value. It's a horizontal line, so all the Y values on this line for every point on the line are going to be the same, 177.22. Likewise, I can do the same thing for the second data point that we looked at, 28.4, 174. So its corresponding point on the regression line is 28.4, 175.31. Again, I just put 28.4 for my X value into the regression equation, and out comes 175.31. This is the corresponding Y value. And I can have a corresponding data point for the mean. So here we have the data points that correspond on the regression line and the mean line to the actual observed data points that are forming our scatter plot. Now, Now it's time to do with the numbers. So explained deviation is the distance between the regression line and the mean. So for the first data point, that's going to give us a value of 0.98. Okay, I took the y value from the regression line and subtracted out the line from the mean. So 178.2, which is the y value for that data point on the regression line, subtract out the y value for the point on the mean line, 177.22, and that gives me the 0.98. Likewise, for the second data point, the explained deviation has a value of negative 1.91. Notice that in the first instance, our explained deviation is positive. In the second instance, our explained deviation is negative. The negative sign just tells you that the data point that you're looking at is below the regression line. If the values are positive, then what you're looking at is a data value that's above the regression line. And that's what we see here on the screen. Now, unexplained deviation is the distance between the data point and the regression line. So for the first data point that we looked at, that's going to come out to be 3.4. So I take that y value for my data point, subtract out the y value for the corresponding point on the regression line, and I get 3.4. Likewise, for the second data point that we looked at, the value comes out to be negative 1.31. Again, notice how the data point that's below the regression line comes out with negative deviation, whereas the one that's above the regression line comes out with positive deviation. Total deviation is simply the distance between the data point and the mean. So for the first data point, that's going to be 4.38. For the second data point, that's going to be negative 3.22. Now, notice how I can get the same value. If I take, for the first data point, 181.6 and subtract out the 177.22, that's that total distance there, I get the 4.38. But notice that if I take my explained and unexplained deviation values, 0.98 and 3.4, and I add them together, I get the same value for total deviation, 4.38. The same thing works for the other data point. This is important to note because what it means is that our graphical explanation is consistent with our numerical explanation. This is mathematically consistent. So this is how you actually pull out the numbers for deviation for individual data points. This then brings us to the concept of explained and unexplained variation. So as we just saw, total deviation is the sum of explained deviation and unexplained deviation. We represent total deviation, explained deviation, and unexplained deviation with these mathematical symbols that you see here on the screen. So total deviation is the distance between our data point, represented by the y, and the mean value, represented by y bar. Explained deviation is the distance between the regression line, represented by y hat, and the mean value, represented by y bar. Unexplained deviation is the distance between our data point and the regression regression line. So that's the y minus y hat. Now notice that if I actually combine like terms here on the right side of my equation, I have y hat here minus y hat here. So y hat minus y hat gives me 0. So those go bye-bye. And I'm left with y minus y bar, which is what I have here on the left. So this equation actually is algebraically consistent. It makes sense. Well, at this point, suppose that I then take my values for total deviation and I take the sum of the squares of that value. So then that would be mathematically represented by what you see here on the screen. Sigma, the difference of y minus y bar quantity squared. This is actually the total variation for our regression equation or our regression model. I can do the same thing with explained deviation. Take the sum of the squares. And then that would give me the explained variation. Likewise, for the explained deviation, I can do the same operation. And then I would get unexplained variation. So then it makes sense that if the total deviation is the sum of the explained and unexplained deviations, that the total variation would then be the sum of the explained and unexplained variations. So this is an important relationship that comes from actually addressing, making and using statistical models. The total variation in our model is the sum of the explained variation and the unexplained variation. Now, to actually quantify this, we use what's called the coefficient of determination. The coefficient of determination is the amount of variation in y explained by the regression line. So this is the explained variation in our regression model. Explained variation is simply a part of the total variation. So if we divide the one by the other, then that gives us the fractional portion, or the percentage, if you will, of explained variation in our model. So if we substitute back in the mathematical equivalents for explained variation and total variation, what we get is actually the calculation for our R-squared value. So R-squared is the coefficient of determination. It reveals the amount of explained variation in our regression line. Because the total variation cannot be greater than 1, we simply subtract the explained variation from 1 to get the unexplained variation in our model. So this value of R-squared, this coefficient of determination, is simply a proportion of the variation in y that's explained by the linear relationship between x and y. Let's look again at our regression equation for shoe print length and height. So our linear correlation coefficient R is 0.847. That means R squared is 0.847 squared, which comes out to be 0.717. This means that 71.7% of the variation in our y variable, which is height, is explained by the linear relationship between shoe print length, which is our x variable, and height, which is our y variable. And that concludes our lecture for section 4. Now we're ready to dive in to some really good stuff here in section 5, where we're looking at multiple regression. The key idea in multiple regression is that we're analyzing a linear relationship that involves more than just two variables. So this involves finding a multiple regression equation and then using values of an adjusted R-squared value and the p-value to measure how well the multiple regression equation fits our sample data. Multiple regression equations are simply linear relationships between a response variable y and two or more predictor variables, which are our x variables. So we have more than one x that feed in to give us the one y that we cut out of our equation. Here's the general form of the multiple regression equation, again represented with y hat. We have an intercept at the beginning, b naught, but then we have b1, x1. So b1 is the coefficient for the first predictor x variable, b2 is the coefficient for the second x predictor variable, and so on and so forth for as many variables as we need to make our equation. Now, we need to be aware of some notation when dealing with multiple regression equations. N we are familiar with. It's the sample size. K, in this instance, is the number of predictor variables. So notice in the general form how that final term, b sub k, x sub k, the k just says that this is the number of predictor variables. So if we have an equation that has 4 predictor variables, or 4 different x values, then we're going to see b sub 4, x sub 4 as the final term in our general multiple regression equation. Y hat is the predicted value of y. Notice there's only one y, okay? So the x is the input. X is what we put into the equation. It's the predictor variables. The response variable is the one value that comes out in response to us putting in all of these values for predictor variables. So the predictor variables are values we put in to make a prediction. The response variable is what the response of the equation is to us putting in the values for the predictor variables. Let's look at an example. Let's say we have some data here, and we're going to look at the height of fathers and mothers, and then the height of daughters, and then we're going to ask ourselves, can we actually predict the height of the daughter given the height of the parents? Interesting question. Well, let's see if we can find the multiple regression equation that will help us to make that prediction. We're going to use software to generate our regression equation. Okay, now I know this is going to disappoint some of you who like the old school method. I'm sorry, we're living in the 21st century. You really need to step into it. So let's just use software to generate our regression equation. When we do that, here's a summary of the results. Notice that we have here at the top our regression equation. It's listed out to so many different variables. So let's just say we're going to take 3 decimal points for our coefficients. That gives us a regression equation. D equals 7.454 plus 0.164F plus 0.707M. Here, the D in the equation is the height of the daughter. The F is the height of the father, and the M is the height of the mother. Notice that the intercept and the coefficients for father and mother, that these values are actually listed here in the table as well as above in the listed regression equation. Sometimes I find it easier to look at these values here when I'm actually trying to round values out, because it's kind of easier for me to see the number separated from everything else around it like it is up at the top. So 7.454 is the intercept value, and then the coefficient for the father, 1.64, and the coefficient for the mother, 0.707. This then forms our regression equation. We find our p-value for hypothesis testing here. Now, I know that we've also been looking here at the bottom of our parameters table for the p-value. And in this instance, the p-value is the same here as it is here in our ANOVA table. And ANOVA stands for Analysis of Variance. In this instance, they are the same. When we're dealing with simple linear models, those p-values will always be the same. But now we're dealing with multiple linear regression models, so those p-values could be the same as they are here, but more often than not, you're going to find those p-values are very different. So then the question becomes, which one do we use for hypothesis testing? And that's why I'm pointing you to the ANOVA table. You want to use this p-value for your analysis. So don't use the one that's marked here in the yellow. Use the one that's marked here in the purple. Now look at the bottom. We actually have, well, 2 r-squared values. What's this? Seriously, we've got 2 r-squared values? Where did this come from? We actually have multiple coefficients of determination when we're dealing with a multiple linear regression model. Multiple coefficient of determination, r-squared, is a measure of how well the multiple regression equation fits the sample data. Okay? It's very similar to what we saw with the r value with the simple linear regression model. So a perfect fit for the data would give us an r-squared value of 1. Here's the equation for calculating r-squared. Notice it's the same as what we saw before for the single coefficient of determination. There's no difference there. But we have another r-squared value listed, which is the adjusted coefficient of determination, or the adjusted r-squared value. This is the multiple coefficient of determination that's been modified to account for the number of variables and the sample size. So here's how we modify it to make that accounting. And you can see here, it looks a little complicated, but it's not really. So remember, n is our sample size, and k is the number of predictor variables in our multiple regression equation. Typically, we want to use the adjusted r-squared value, and it's one of the 3 factors that help us to guide us in selecting the quote-unquote best multiple regression model. again, we want to use that adjusted R-squared value. It provides a better accounting for explained variation. Okay? There are many people out in the real world who simply take that R-squared value to judge how well their model fits the data. But the thing with using R-squared is that its value will change, usually an increase, with the number of variables and sample sizes. And so that's why we want to use the adjusted R-squared value, because it's a more stable value and a more realistic look at how well the model fits the data. It's a better accounting for explained variation, given differences in the number of variables and sample size. So make sure you use that adjusted R-squared value. We want to measure overall significance with the p-value. So the p-value is the second of the three factors that we're going to use to select our best model. Generally speaking, as we've seen with hypothesis testing, the smaller the p-value, the more significant the combination of variables our model is going to have. So smaller p-values are better than larger p-values. However, you never want to use a model with high p-values. Okay. Now, what's high and low? That's relative. Okay, those are relative terms, and you measure that based on the p-values for the other regression models that are in the list that you're going to be considering. We'll look at that in a moment, and when we do, I think that'll make much more sense as to how to measure what relative means. Lastly, you don't want to forget sound judgment. There are a lot of people in industry who simply use a computer program, and there are computer programs that will run multiple different types of models and then give you a comparison. And typically, the computer software will pick the one with the highest adjusted R-squared value. This is not the way to make the selection for the best models. Okay, so people who don't know what they're doing, they'll just take what the computer's giving them, and with a blind sort of faith, they just waltz off and just take that, when in actuality, the model that they're using may not be the best one. Use some sound judgment, okay, to decide if the model that you're taking is really the best one. Okay, sometimes the best model is not the one with the best R-squared, adjusted R-squared value, or the best p-value. Okay, sometimes you can get away with, you can use a model that has fewer variables in it. It has similar but not quite as good adjusted R-squared value or p-value, but it's often better to use a model with fewer variables than one with many variables. Okay, because complexity often just makes things more complicated than they need to be. And also consider that when you actually make these models, they're typically not for one-time use. Okay, you're going to be refining these models as you go along with time. So you're going to be continuing to collect data to support that effort. Well, all of this data collection, it requires resources, time, money, manpower. So you want to make sure that you minimize the number of variables you have in your equation, because then this will allow you to minimize the number of resources you need to keep that model up to date. The model must also make sense from both the creator and user perspective. So it's got to make sense for the user to use it. Okay, and again, this is where simplicity comes in. It's more likely that someone's going to use a simple model than a complex model. But it has to make sense from a creator perspective as well. And what that means is there's got to be some type of a relationship between the predictor variables and the response variables that makes sense. So again, a computer is not going to be able to judge that. You've got to use sound judgment in addition to using the values that the computer can give you to select your best multiple regression model. Let's use the same factors that can help us to decide among several different models. These same factors can help us to evaluate a single multiple regression model. So let's look at the regression model that we just made that predicts the height of a daughter given the height of the parents. So first, the adjusted R-squared value for that model is 0.637. Okay, this is not a really super great value, okay, which we need to get like 80, preferably above 90%, have a superior value for adjusted R-squared value. But as adjusted R-squared value goes, it's decent. Okay, it's something that we could potentially use to make a prediction with. The p-value was listed in the results as less than 0.0001. This means that the number is far less than 0.0001, which is practically zero. That 0 is the best p-value you can have. So this is an outstanding p-value for our model. Height is a genetic trait, so it makes sense that the height of the parents could be used to predict the height of the daughter. So by itself, our model looks good for making predictions because we got all the 3 criteria for making that model met. Let's expand our earlier data set for shoe print length and height to include 3 other variables. So now instead of making a simple linear regression model, we're going to make a multiple linear regression model. So we're going to add in some other variables into shoe print length so that we come out with our prediction for height. For example, age. People, have different, heights and shoe print lengths for age, so we're going to throw that one in the mix. Foot length and shoe size. These are all variables that could play in with the height. So let's take a look at this. Here we have a table that's listing the adjusted R-squared values and p-values for models made with different combinations of these predictor variables. So, for example, in the first row, underneath the headings, if I make a model that has just age in it, then my adjusted R-squared value is 0.1772 and my p-value is 0.004. Likewise, I can make a model that has just foot length and its adjusted R-squared value is 0.7014 and its p-value is 0. And go on down the list. The last model in the column, I'm using all 4 of my predictor variables to make a model. So I have age, foot length, shoe print length, and shoe size. Now, one of the things you need to understand about model making with statistics is that you can make a model that tells you anything you want to hear. So if you want to make a model that includes all of your predictor variables, you can do that. It may not be the best model, and we're not going to know until we make other models and then do the comparison between the different models. That's how we make the selection to find out what the quote-unquote best multiple regression model is. So how do we make the decision with this list here? Well, first, we're going to look at this first model up here at the top, okay? And we can actually eliminate this model. Look at its adjusted R-squared value, 0.1772. Compare that with the other adjusted R-squared values in the list. I mean, it's off in a field by itself, and it's way low. We want adjusted R-squared values to be as close to 1 as we can get. This looks like it's about close to 0. So that right there says we're going to eliminate it. But look at the p-value. The p-value is also the highest p-value in the list. In fact, it's the only non-zero p-value in the list. So it's got these 2 strikes against it. We can go ahead and just eliminate this model. So now we've got 4 models left in our list. So what do we do next? Well, next, let's look at these next 2 models that are last in the list. They have the highest adjusted R-squared values of any model in the list. But they also have more predictor variables than any model on the list. So the p-values are the same for all the models that are left. So we can't really use that. We have to look at the adjusted R-squared values because that's where the differences are. Notice that the values that we're getting, the 0.7585 and the 0.7484 for our adjusted R-squared values, are not really that much higher than the next highest on the list, the 0.7014. But look at the complexity that the model introduces. One model has 2 predictor variables. The other model has all 4. So this extra level of complexity it influences us to make the decision of saying, well, we're just going to go away with these models because they offer more complexity. But in exchange for that complexity, we don't get an appreciably better adjusted R-squared value or better p-value. Of course, you're not going to get a better p-value because 0 is the best you can get. But we still have 2 models left to look at. So they each only have 1 predictor. So we can't use this simplicity factor to distinguish which one we're going to take. The only real difference between them is the adjusted R-squared value. So we're going to take the one with the higher adjusted R-squared value because everything else about these two models is the same. They have the same level of complexity. They have the same p-value. The only real difference is the adjusted R-squared value. So we'll just take the one that has the higher adjusted R-squared value. Now, look at the models that we have in the list. The model that we ended up selecting as the best model doesn't have the highest adjusted R-squared value. So if you're following that little piece of software that's comparing models for you, and it's just simply giving you the model with the highest adjusted R-squared value, you're not going to come out with the best model. You have to do the comparison by using sound judgment. Now, looking at this model by itself, foot length and height. What do you think the difference is between foot length and height, a model that's using those two variables, and the model we made earlier that's using shoe print length and height? Probably not a whole lot of difference. There's probably really strong correlation between foot length and shoe print length. People aren't going to wear shoes that are too small for their feet because their feet can't fit into them. But they're not going to use shoes that are too big for their feet because they're going to make it really funky to walk in them. So there's going to be a really strong relationship. So it kind of makes sense that a model that's using foot length as a predictor variable would come out to be a good model. How useful is this in the real world? Well, are you able to measure the length the foot length of a criminal after the crime has been committed? All you've got left is the shoe print length. So you know that the foot length is somewhere around the value of that measurement, but you don't really know like how much space is there between the actual foot and the shoe. You don't know how snug it is, so it's not really a very useful model when we come out with. But as far as selecting the models go, it provides a better prediction than any of the other models in the list. This brings us to dummy variables. Okay, so there are many applications that involve a dichotomous variable. A dichotomous variable is one which has only two possible discrete values. So we see this all the time: male, female, dead, alive, on, off, in, out. So many different combinations for dummy variables, but that's really what dummy variables are. So what we do is we take these dichotomous variables and we represent them mathematically with a 0 and a 1. And we do this because discrete values, remember discrete values, this is categorical data. And we can't put categorical data into a mathematical operation. So the way that we represent this in a mathematical equation is with what's called a dummy variable. And the dummy variable is simply the dichotomous variable that we represent with either a 0 or a 1. Let's go back to looking at the example that we looked before, but now instead of, looking at that. So now instead of looking at the height of the daughter, we're going to look at the height of a child. So they're in the table. I need to make a correction. It shouldn't say daughter, it should say child, because some of the children are actually male. So I need to go back and make that correction. But the data itself is still good. So what we're going to do is we're going to put this data into our software to run our multiple regression analysis. But we can't put the M's and the F's in, because then that's just going to give us, the computer won't accept that. It doesn't understand that. So what we have to do is replace the M's and the F's with 0s and 1s. And it doesn't matter which way we go. We can do it either way we want. We just need to be consistent with how we use the equation after we set it up. So let's just put 0 in for females and 1 for males, and we'll just use that convention. So we make our multiple regression equation, and here comes out the results. So here's our equation, and 25.6 plus 0.377m plus 0.195f plus 4.15g. We get that regression equation from the top of our results window. Now notice that we can also look here to get the values of individual intercepts. So I can look in two different places to get those values. If I'm looking for just the individual value, I'm tending to use the ones in the table because they're not all crunched together like they are up at top. It's easier for me to read them. So if we have a mother that's 63 inches tall and a father that's 69 inches tall, then the daughter is going to be 62.8 inches tall. How do we figure that? Well, here's our regression equation with the values put in. Remember that the height of the father was given as 69. Height of the mother given as 63. So those values naturally are going to come in here. But then the 0 that we get here is the gender of the child. Okay, and remember the convention we used when we set up the equation, that 0 is female. So I have to be consistent with that convention when I use the equation. If I'm looking for a prediction for a daughter, then I'm going to put a 0 in for the gender variable. Punch that out on the calculator and we get 62.806, which rounds to 62.8. Likewise, if the same two parents have a son, then the prediction for the height is 67 inches. And you can see the math for that right here. Notice that I'm putting a 1 in for my dummy variable because now we're looking at a male instead of a female. Out come the numbers, add them together, and I get 66.956, which rounds to 67. So this is the way that dummy variables are used in a multiple regression equation. And that brings us to the end of this lecture. If you have any questions, you know where to find me. Otherwise, I will see you in class. Thanks for watching.